Hi guys, and welcome back to another lesson on the Noble Chemist. Now, for the next series of lessons, we're going to talk about quantitative chemistry and specifically referring to stoichiometry. Now, in order for us to jump into the quantitative aspects of chemistry and the elements and the ratios in which they react to one another, we need to have a basic understanding of the periodic table. Now, after my stoichiometry lecture series, I will then jump into the periodic table and explain some of these concepts that you can currently see on this periodic table itself. So, for example, we are going to then look at some of the different key aspects: density, atomic radius, electronegativity, melting and boiling points, ionization energies, and so on. Okay, we're also going to look at something that's quite cool about this interactive periodic table app is that you can go and look at the history of discovery of some of the elements. As you increase your timeline, you can see most of the elements were actually discovered between the 1800s and the 1900s. You can even look at the temperatures to know in what state a specific element is at a different temperature. So here we are at minus 273 degrees Celsius, and as we increase our temperature, you can see some of these elements that were solid turns to liquid, and the higher we go in temperature, you can see almost all of your elements are in gas phase. So that's quite interesting. So it's nice to play around with, and you can also look at the general classification and characteristics of metals and where they are situated in your table, and those of non-metals. Okay, but that we'll discuss in more detail later on. So you can download this app. It's from the Royal Society of Chemistry. You can just go onto your Play Store and type in interactive periodic table, and you will see this one. Okay, what I want to actually get to today is I want to talk to you about carbon. And why carbon? Okay, carbon because most of the definitions that we derive today in stoichiometry are based on carbon and the mass of carbon, and also is focused around this whole idea of the units, the mass atomic units of carbon. So you will see when you look at an element on the periodic table, it normally has two different numbers. So this number here is defined as the atomic mass of the carbon atom. So it's measured in atomic mass units, and it can also be known as grams per mole. So it's the grams of carbon per mole. Okay, so we're going to look at what that really means and what is a mole and what's the definition of that. And so just keep that in your head now. We're going to look in the next video, we'll look at the mole concept, and then we'll also look into Avogadro's number. Okay, this number here, 6, represents the atomic number, and that means that you have 6 electrons and 6 protons inside of your atom, and we're going to look at that in more detail if we discuss the periodic table. So if you click on carbon, it will give you a lot of different characteristics and even history. For example, here they tell you the meaning of carbon, the classification thereof, the following allotropes, different forms that you can find in nature. And if you look at the atom diagram, you will see that this yellow part here represents the nucleus, and around the nucleus you have your electrons. So this is just a schematic diagram to get you thinking in that direction, but it's actually much more complicated than this. So you can see that you have 1, 2, 3, 4, 5, 6 electrons, and in the outer shell you only have 1, 2, 3, 4 electrons in the outer shell, and that will be known as your valence electrons. Okay, that's the electrons that normally partake in a reaction, but we're going to discuss that in more detail. So you have 6 electrons. Then inside of your nucleus, you have 6 protons. And to work out the number of neutrons, you have to take this molar mass or atomic mass and subtract the atomic number to work out the number of neutrons. So you will have that minus that, which is 6 neutrons inside of your nucleus. Remember, neutrons are neutral in charge, electrons are negative in charge, and protons are positive in charge. Okay, so that's just a few things. You can go and look at the rest of the information. Now, what I want to talk to you about today especially is what is the meaning of the atomic mass unit. So I'm just going to open up this dialog box here and I'm going to make a few notes. So first of all, what is an atomic mass unit? Okay, so we need to define what this is. Okay, it's also known as an AMU. So what is a atomic mass unit? So one atomic mass unit is also equal to 1 Dalton. Okay, and don't worry about where the definitions are from at this point in time, but just know that it's equal to 1 Dalton, and that is basically equal to a 12th of the mass of a neutral carbon atom. That's the definition. Okay, one atomic mass unit is equal to a 12th of the mass of a neutral carbon atom. Now, how do you know what the mass is of one carbon atom? And we're going to use the information provided on the periodic table to help us to answer that question. So on your periodic table, you can see that the atomic mass is given as 12.011, and like I said earlier, okay, we can also denote this as grams per mole. Okay, and I'll explain this in more detail when we talk about how to work out the mole calculations and how to calculate this value. So now you have grams per mole. So if you want to get the mass of one carbon atom, you will say, well, you've got 12 grams per mole, and we are going to take this grams per mole and divide it by Avogadro's number. Okay, and I will introduce Avogadro's number to you with an explanation. But for now, you just need to know that Avogadro's number is basically a constant, and it's 6.02 or just 6, but it depends on how accurate you want to work, times 10 to the 23 atoms per mole. So what that means is inside of 1 mole, and this is going to be very important, I'll explain that, but inside of 1 mole, okay, you have this amount of particles, and that is Avogadro's number. That's what the definition of this is. Okay, that's what we define a mole as. So inside 1 mole of carbon, you have 12.011 grams. Okay, and inside 1 mole of carbon, or 12 grams of carbon, you have this amount of atoms. Okay, so to work out the mass of 1 carbon, if I just continue my calculation, it will give me 1.99 times 10 to the negative 26 kilograms per atom of carbon. Okay, I just want you guys to see how big the numbers are that we're working with. This is 10 to the power of 23. So if you think of 1 million, a million has 6 zeros, okay? So think about how many zeros this is. This is a very big number of particles, okay? It's tremendously big. So what is the mass of one carbon atom? And there you go. Now look at that number. It's negative 26. So you can see how very, 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 very small of a mass that is. Okay, so it's actually quite light. So that's the mass in kilograms of one atom of carbon. Okay, so coming back to defining what an atomic mass unit is, 1 mu is equal to a 12th of the mass of one carbon atom. So if you, let me just leave that. So if you work this out, it will give you an answer of 1.66 times 10 to the negative 27 kilogram. Okay, so that is that's the mass in kilogram of one atomic mass unit. Okay, and so you don't have to overcomplicate this for yourself, as long as you remember that you can get the grams per moles from the periodic table. You can divide that by the Avogadro's number, which is always a constant, okay? As we will define in the next video, where 1 mole is equal to that amount of particles, and that particles can be either atoms or ions or even molecules. Okay, so that is atomic mass units. Now, just to quickly finish off this lesson, I quickly just want to highlight the difference between what we just did. We talked about atomic mass, right? So remember that atomic mass, we referred to atomic mass unit, okay? That should be a U. And we said, well, we talked about atoms. Okay, in this case, we can talk about various particles like ions. We can even talk about electrons. Okay, but now, if we talk about molecular mass, molecular has to tell you that we're working with molecules. So now, if I were to look at a water molecule, now remember, this is a water molecule, right? You have an oxygen, you have 2 hydrogens. Now, each of these elements, okay, have their own atomic mass units as specified on the periodic table. So if I can just go back and show you, hydrogen has a atomic mass of 1.008. Now you can see this is quite 3 decimal places, so it's very accurate, but sometimes in high school level we just use 1 or 1.0. So if you were to work out the molecular mass of this whole system, and we sometimes refer to as the relative molecular mass, and the reason why we use relative is just to show it relative to the carbon, right? The mass of carbon, but we are just going to denote it as Mr. And the reason for that is just to avoid the problem of having units in your calculation. So the molecular mass of a water molecule is going to be the mass of 2 hydrogens. Can you see there's 2 hydrogens? Okay, so it's going to be the atomic mass. Okay, so I'm just going to refer to it as Mr of 2 hydrogens. Okay, and you're going to add the relative molecular mass of 1 oxygen. Okay, so let me just write that out so that that makes more sense. So your atomic mass of hydrogen, and there's 2 of those, and then you're going to add, and if you just look at oxygen here, if I just look at oxygen, you can see it's 15.999. Okay, very accurate. And there's only 1 of those, so I'm just going to times it by 1. So when you add these values together, it should give you the relative molecular mass. So I'm just going to work out the accurate one. But like I said, you don't always at school level have to work and too accurate in terms of your decimal places. So if you can leave it to 3 decimal places, or in this case we can take it to 2 decimal places, and that would be your relative molecular mass. If you were referring to just plain and simple your molecular mass, then you would put your unit and you would say that would be grams per moles. Okay, so that was molecular mass. Now there's another type of mass known as a formula mass. Now, formula mass refers to ions. Okay, so molecular mass refers to molecules, and now we're going to look at ions. So if you look at your periodic table and you look at your different elements, remember that ions is a combination of a metal plus a non-metal. Right? So an example of that would be sodium chloride. Sodium is the metal, chloride is the non-metal. So if I go and add to get the relative formula mass, okay, and I'm just going to denote it in the same way because we use the same principle. So relative means I'm not going to add my unit, okay. So sodium on the periodic table is in group 1. You can see there's 1 of them, so that's 22, not 29, 22.990, plus if you search for chloride, which is in group 7, you can look at that, 35.45. Okay, so if you add those 2 up, grab my calculator, you will get a mass of 58.44. Okay, that's the formula mass of sodium chloride. Okay, if we were talking about the relative formula mass, that's the relative formula mass. If we're talking about normal formula mass, you can then go and say, well, that's grams per mole. Okay, another important thing that I'm not going to discuss in too much detail now, but when we talk about relative atomic mass, so we looked at atomic mass and we also defined what atomic mass was. But I just quickly want to illustrate something by the definition of relative atomic mass. What does this mean? So, relative atomic mass refers to the abundance of certain isotopes in nature. Okay, I was thinking about this now since we're talking about chlorine. Now, chlorine, you can see, has an atomic mass of 35.45. Okay, so if we look at chlorine and we look at its relative atomic mass, which is 35.45, here you can see. And also, if you look at some of the other information given about chlorine, you can see that it has 2 key isotopes. Okay, so if you click on isotope, they give you the definition of what it is. So An isotope is atoms of the same element, which in this case is chlorine, with different numbers of neutrons. Okay, so you have different neutrons inside of the nucleus. So if I would go and look at the two examples, you have chlorine 35 and chlorine 37. So you can see the mass number is different. So how do you now calculate the relative atomic mass? And that's where it's important to look at the natural abundance of these isotopes in nature. So if you look at chlorine 35, okay, the atomic number is 17 for both of them. If you look at chlorine 35, it has a natural abundance of 75%, okay, which means that all of chlorine that exists on Earth, 75% of the chlorine is chlorine 35, okay, and only 25% is chlorine 37. So when we work out the relative atomic mass, okay, we take into account the percentage abundance of these isotopes. So if you work out the relative atomic mass, there's a formula for this. So you would go and say, well, 75% of all the chlorine is chlorine 35. So you times the percentage by 35. And you add the 25% that all belongs to chlorine 37. Okay, and if you go and you work out this, then you get a value of 35.5, and that is basically this rounded off 35.45 to 35.5, and that is the relative atomic mass of chlorine. And you can do the same for some of the other elements. So if you go back and you look at other elements that will have isotopes, and normally you get to learn them. But then another very common one is bromine. So if we go to bromine and you go and look at its isotopes, you can see the key isotopes is bromine 79. Okay, they don't actually show the other isotopes because it's 50-50 for both of them. Okay, so we don't I see they didn't show that in this table, but you can even look at hydrogen. Okay, hydrogen has 3 different isotopes. Okay, that's normal hydrogen, then you have hydrogen with a mass number of 2, and then you have tritium. Okay, so you have hydrogen, deuterium, which is the 2, and then tritium that has a mass number of 3. Okay, and that's how you work out the natural abundance. You add them together and you get the relative atomic mass. Okay, so I hope that was useful. In the next lesson, we're going to look at the mole concept, and we'll also then discuss Avogadro's number, and then we'll look at stoichiometry calculations from there on forward. Have a lovely day, and then I'll see you again.